So today you have Charles from NVIDIA, Julia from Element 84, and then Naty and myself from Coiled. And yeah, we're going to be hopefully having a good tutorial here. So I'm going to provide a brief outline. We've got overview notebook. So Dask is a large project. So even if folks have, it's pretty common for folks to have experience with sort of one subsection or some segment of the project. So this is going to provide an overview, a broader overview of the project at large. Also maybe a refresher, hit off some rust if it's been a while since you've used Dask. Then we're going to move on to custom operations. Then we're going to dive a little bit and poke at the distributed scheduler in the third notebook. And in the fourth notebook, we're going to work through sort of a real-world example where we're going to talk about performance optimization.
Right. So a lot of people here are already pretty familiar with Dask, but I'm just going to go through a quick overview of why you might want to use it, what the high-level and low-level APIs look like, and just like an overview of the schedulers that enable parallel execution of the graphs that these APIs create. Right, so for those that don't know, Dask is a flexible open source library for parallel and distributed computing in Python. It's generally used to scale the existing Python ecosystem. You're probably looking into Dask if you're trying to enable parallelism and larger than memory computations. You're probably a user of NumPy, pandas, or scikit-learn. It offers familiar APIs, so there's relatively minimal code changes when you're trying to scale existing workflows over there. It also offers a pretty flexible cluster system, so it's relatively easy to start on your laptop and scale out without much change. And it has a ton of good built-in diagnostic tools and a dashboard that make it relatively easy to troubleshoot and generally look into iterating and improving performance. Right. So from a high level, Dask is comprised of two main components. We have the collections, which extend common interfaces like NumPy, pandas, or Python iterators, and these create task graphs, which then a scheduler uses to compute in parallel, but also sequentially, if you're interested in that. Right, so to give like an idea of what task graphs look like, maybe let's use just a pure Python example. So this is just some atomic functions like taking in an argument and incrementing it, taking in multiple arguments and aggregating over those. Something like this could be represented in Dask with a task graph that looks like this. So circular nodes are representative of Python function calls, so these increment calls would be here, and square nodes represent the objects that these functions can return. And these objects can also be piped as input into another task. So we see that these increment tasks return something that's then pushed into this add function call. So Dask collections can either be high level or low level. High level collections look something like mimicking common PyData APIs such as NumPy arrays, pandas DataFrames. We have bags for iterators. And then there's low levels such as Dask delayed for when these high level APIs don't necessarily work for what we're trying to do, and we maybe are trying to do something more like suited to something fine-tuned. Right, so I'm going to go into two examples, Dask array and Dask delayed. So Dask arrays are chunked n-dimensional arrays. Easy way to think of them is basically a collection of several NumPy arrays. Dask arrays implement a large subset of the NumPy API, and so in most cases you can generally use this as a drop-in for NumPy. And yeah, like I said, it's easy to think of it as like several NumPy arrays all concatenated together into chunks. So if we look at what it would look like between NumPy and Dask create array, here we're making a random array using NumPy random. And that's, exactly what we'd expect. In Dask, this happens nearly identically, but notice that we need to specify this chunk argument to tell Dask how to break this array up into chunks, individual NumPy arrays. And yeah, we have this nice little wrapper here, just displaying the chunk information, size of the array in the chunks, some stuff about data types. Yeah. So Dask arrays have the same look and feel of NumPy arrays. Generally, things that you would expect to be able to do on a NumPy array, you can do it on a Dask array. So here we can just pull the data type and shape. But notice, one big difference is that they're computed lazily. So this doesn't actually give us any values. It gives us a task graph that we then need to specify to be computed. So we can view that task graph using the visualize method. So now we see that we're doing function calls to this random sample function that compose each of the chunks of this array. And then to actually compute a task graph, we would call the compute method, which we will go into more detail on later. And so once we've done that, we see now that we have a familiar NumPy array that we can operate on as we would in NumPy. Yeah, so like I said before, supports a large subset of the NumPy API, so things like binary and unary operations, standard slicing and indexing, and then just general array protocol are all there. But also, I encourage going to the Dask Array API docs to get a sense of what Dask does and doesn't do and how that may differ from NumPy's API. So yeah, using this, we can build up more complex computations using the same familiar NumPy API that we'd expect. And like I said before, this is all done lazily, so we don't actually have a result here. We can visualize the underlying task graph, which should be a fair bit more complicated now. We see the same underlying random samples that comprise the initial array, and then a variety of operations that lead us to eventually aggregate it, right? And then once we actually want the result, we'd call compute on that. And it's worth noting that even though I've been using NumPy for these examples, other array-like libraries that implement the NumPy array interface can be used here. If you're working with sparse data, you can use PyData sparse. If you have GPU accelerators available, you could use CuPy as the backend. And the same goes for other collections such as DataFrames. Yeah, so sometimes we want something a little bit lower level. Maybe these high-level APIs aren't working for what we need to do. In these cases, we can parallelize just standard pure Python functions using the Dask delayed interface. So here I'm going to revisit the same example we had above, but introduce these random sleep commands before we actually return. This might mimic something like I/O, any type of computation that makes a task take longer, right? So we define these, and this, we have like some input data that we're going to increment, do some operations on, gather together, and then aggregate. And if we look at this, this is all running sequentially, so we would expect this to take a while because all of this stuff is happening one after another instead of at the same time. But we know it can happen at the same time. So why don't we try importing delayed and annotating one of these functions. And now we see that instead of the function itself, we have this delayed object, which records the things that we need to compute, so a function and the parameters being input into it. And this is something that we can then later compute on using compute. So if we pass an argument to that function, we also get a delayed object. And once we compute on it, we get the result we would expect. Yeah. We can pass the results, we can pass another delayed object into a delayed function to in turn get another delayed object. Looking at this, we can see what we would expect. So a function call to this lazy increment that returns a result that's piped into another call of that lazy increment that returns the final result. And then computing that, yeah, again, we get the result we'd expect. So now we can use delayed to go back to our initial sequential example and make all of those functions lazy delayed functions. So now when we try to run the exact same thing as before, we instantly get a delayed object. We haven't done anything yet, but we have assembled a task graph that essentially has these leaf nodes, signaling that we can do these increment and double operations roughly in parallel. We can aggregate those roughly in parallel. And yeah, so now when we compute that, we'll see that this takes a fair amount less time than before because all of this stuff is happening in parallel. Again, same with arrays. I'd recommend checking out the documentation for best practices on like when and where you might want to use delayed and how to get the most out of it. So yeah, those are collections. those are generating graphs. The next piece of the puzzle is the scheduler, right? So these graphs alone aren't the results we want. They need to be passed on to a task scheduler that will then compute the result. There are a few different task schedulers. They all compute the same result, but they have different performance characteristics, which we'll get into. So the two major classes here are single machine schedulers that provide some basic features on either local processes or thread pools with minimal setup, or distributed schedulers that are a little more sophisticated. They have a little bit more to them, but they also require a little bit more time and effort to set up, right? So single machine schedulers have three different types that you'd want to use. We have threads. Threaded scheduler executes computations on multiple threads in the same process. This is the default for Dask arrays, data frames, and delayed. In general, this is like a sensible default. This is something I'd say you would want to do on objects that are able to sort of bypass the Python GIL. Yeah. Processes, the multi-processing scheduler, executes computations on multiple sub-processes of the main process. This is the default for Dask bag, I believe. And this is something that you probably want to like be a little bit more thoughtful when you're going to use it. This is something that you might want to use when you're working with pure Python objects, but you do want to avoid like frequent data transfer between the main process and the sub-processes. And finally, the synchronous scheduler executes all computations sequentially in the local thread. This is something that you'll probably find yourself using if you're trying to debug things. Maybe you've set up some Dask code, something isn't working in there, and you're trying to gauge like why something isn't working on a particular chunk or partition. You can set the scheduler to synchronous, and it's relatively easy to set a breakpoint in there and like check out what's going wrong. There are a few different ways that you can configure the scheduler. You can set it globally using the Dask config module. So if you want to set it for an entire script, you could just set that on its own. Or you can use it as a context manager to set it for just a block of code. Or if you want to set it for an individual compute call, you can pass the scheduler argument directly into compute. And it's also worth noting that depending on what scheduler you're using, you can pass additional arguments to it that control aspects of the scheduler. So in this case, since we're using a threaded scheduler here, passing this numWorkers argument indicates that we want to use 4 threads. So the distributed scheduler, despite having distributed in the name, isn't limited to, you can use it on single machines. It's probably better to think of it as more of an advanced scheduler that offers additional features that you don't get with the single machine scheduler, right? So it's comprised of a single centralized scheduler with one or more worker processes, with a client that's used as a user-facing entry point that's used to actually interact with the cluster. We'll go into more detail on this later on. And it has a variety of features, such as like a futures like interface. You can submit tasks to be computed asynchronously on the scheduler. There's some more sophisticated memory management and data locality to optimize memory usage and data transfer. There's adaptive deployments, so you aren't really fixed to a fixed number of workers. You can maybe scale up and down workers depending on what tasks you need to get done. And things like cluster resilience. Again, Dask distributed documentation has a lot more information on some of the benefits and reasons why you might prefer using Dask distributed. But to set it up, at least for like a hello world example, it's very easy to just import from Dask distributed the client, and just passing that with no arguments will create a local client and cluster. And it's also worth noting that there's a dashboard that you can view. And yeah, from there we can do the same things as we would do before. And now this is happening on a distributed scheduler. And then once we're done, we can close that with client.close. Yeah, and so that's like general overview of Dask. The next thing we're going to look into is Dask internals and how to do custom operations. So I'm going to hand it over to Julia.
Thanks, Thomas. All right. So now we're going to be talking about custom operations in Dask. So in the last notebook, we were looking at some of the algorithms that come predefined for different types of Dask collections, like Dask arrays and Dask DataFrames. These include things like mean, max, value count, all the normal kind of like pandas and NumPy, or most of the normal pandas and NumPy methods. But in this notebook, we're going to talk a little bit about how those operations are implemented, and we're going to learn how to construct our own custom operations and optimizations, and get a sense of when you might need to write a custom operation and which approach to take. So there's some documentation here that you can refer to later if you want. So first, let's talk a minute about blocked algorithms. So Charles mentioned the task graphs, and you saw sort of the structure of how this is set up, but I just want to make sure it's clear that Dask computations are implemented using blocked algorithms. So the algorithms break up the computation on a large array into many computations on small pieces of the array. And the benefit of that is it minimizes the memory load, so you can do computations on data that exceed the RAM on your computer. And you can also split up computations so that you can work on larger than memory data sets in parallel, or just, even if it's not larger than memory, you can just work on stuff in parallel so it goes faster, especially if a big cluster. So let's get going. So here's a basic setup of an array of random numbers. And you can see I specified this chunk shape of 250 by 500. So that's the shape of the chunk. And the size of the array is 1,000 by 1,000. So you'll see in this representation here that each of these, there's 8 chunks, and they each have the height of 250 and the width of 500. And so they're kind of stacked up in this particular way to make the total array have the desired shape. So you'll see these numbers floating around, the chunks argument floating around a lot, and sometimes it can be confusing, but oftentimes the graphic is very helpful for kind of orienting yourself and remembering what exactly we're talking about here. So each of those represents a chunk that we can then operate on. So we can look at this calculation that's kind of just kind of an example of some complex computation. It's kind of a toy, but it's just like taking taking this array, adding it with a transpose, taking the sum over an axis, and then doing the mean of that. So it comes down to, I think, one number. And we can break it down and look at the task graph for just one part of that computation. So in this graph, you can see that we have this function random sample that leads to one output chunk that's at the 0, 0 position. So in this above, like, I don't know which direction it goes, but maybe this one. And then the transpose operates on that same chunk, and then you go back to you put the chunk back in the same spot. And that happens for every single chunk in that array. This is a task graph that's perfectly parallelizable. So there's each little chunk can just be operated on and totally in parallel. Nothing that needs to come back together and aggregate at the end. So this is the perfect task graph. And Dask, one of the benefit of Dask is that one of the benefits of Dask is it makes it easy to construct graphs like this using the NumPy-like API. Okay, so custom block operations. These are operations that operate on a per block basis. Each block gets a function applied to it, like the transpose we were looking at above, and the output has the same chunk location as the input. So you're operating on that chunk, putting it back in the same spot. Some examples include custom I/O operations, or just embarrassingly parallel functions where there's no existing Dask implementation. So some custom thing that you do, maybe on your image or something, that there's no existing method for. And these are the docs on this next section, if you want them later. So for arrays, you would set up, if you want a custom operation to operate blockwise, you use map blocks. So for this example, let's imagine that there's no da.random.random, doesn't exist. So we can create our own version using map blocks. So we can import NumPy, and we can make a function that just creates one block and it makes this block of this particular size, 250 by 500. I just chose that. That's the chunk size, but you could choose something else. And then you have da.mapBlocks. You pass in that function, and then you say what you want your output chunk shape and pattern to be, basically. So you want, along the x-axis, you want 250, 250, 250, 250, and the other way you want 500, 500. And then you specify the data type of the output, what it's going to be. And so you end up with the same array. So it looks kind of boring. We've been staring at this a lot. But hopefully you can see that you can sort of construct any type of operation in this using this pattern, as long as it's totally parallelizable like that. And we can look at the task graph. And we'll see that we have our random sample, which is the name that I gave to this function. And then each function outputs to one chunk. So let's dive in a little bit to the chunks argument. In the example, we explicitly declared what the size of the output chunks will be, the 250, 250, 250, 250, 500, 500. That means 8 chunks, each with this 250, 500 shape. You also see the chunks argument written out in the short version, where it's 250 by 500. These mean the same thing, but specifying the output chunks is very useful when you're doing operations like map blocks, because then you can guarantee that the output will have the right shape. And having the right shape lets you change the other operations. So we're going to be, there's some information when you're doing custom operations that you need to tell Dask, so that Dask knows what the what type of output it's going to get out of your operation, so that you can do things like you could do this function, this custom random function that we wrote, and then you can call .transpose on it. And that's because you tell Dask, like, this is what it's kind of going to look like at the end. So that's something that comes up in custom operations that you don't have to do when you're using the out-of-box ones, because Dask internals handles that for you. So dtypes is another one of those things that we need to tell Dask, because otherwise Dask doesn't know whether the output's going to be an int or a string or whatever. Okay, so next we're going to apply map. So in that example, we were creating an array using map blocks from scratch. So we weren't starting with any array. And then in this next example, we're going to have two Dask arrays with the same, and we're going to operate on those using a custom operation. So these are two Dask arrays that have the same number of blocks, but different shape and chunk sizes. So this first one, let me just print them out so you can see what they look like. So the first one has shape, has 1,000 items in it, and the chunks have a shape of 100. So it has 10 chunks, and they're all in a line, but they each have size 100. And the next one has the same exact shape, but the total array has 100, and the chunks is each chunk is size 10. So this feels contrived potentially, but it is a thing that people have, maybe some metadata or some other array where every item maps to something that's bigger in a different array, and this can be a useful pattern for that, as long as the shape of the chunks matches, or the pattern of the chunks matches, I should say. So we can pass these arrays into map blocks using a function that takes 2 inputs. This is just kind of an arbitrary operation that I made up, that where each array we're going to take the max, and then we're going to return return an array of size 2 where the items are the two maxes. So, and then we can write a da.mapBlocks that takes that function, takes the inputs of the 2 different arrays, and then says what the output chunk size is. Okay, so you can see that each of those, we have the setup of the, right. Each of those A and B are getting fed into this one function and then output to one chunk. Okay, I'm just going to note this, but we're not going to have an example about it, that there's special arguments called block info and block ID that you can use within the mapBlocks functions, and they let you keep track of where you are within the total operation. So which chunk you're looking at within the nested function. So block ID gives the index of the block within the chunk, and block info gives a dictionary where the integer key for each, yeah, it gives a dictionary. You I feel like when I use these, I normally end up printing them out within the nested function, so I can sort of like get my bearings a little bit. So they're not maybe entirely intuitive, but they are very helpful when you need them. So this next section is about Dask DataFrame. It's going to be the same concept, but rather than talking about arrays, we're talking about data frames here. And so the equivalent of map blocks in data frames is map partitions. Here's an example. Yeah, that's basically we're going to construct a data frame, and then we're going to check the sum of two columns greater than some threshold. Okay. And yeah, it's the same. Basically, I think the only thing I'm trying to show here is this. It's the same type of task graph where it's totally parallelizable, no mapping and no aggregation. Yeah.
Chunks, blocks, and partitions, are these all synonyms?
Yeah. Chunks, yeah. I mean, chunks and blocks are what we use in array land, and partitions is what we use in data frame land.
But conceptually, they're the same.
Conceptually, they're the same. And I wish they were all called the same. Yes.
When a data frame is partitioned, are some partitions having different columns than others?
No.
No.
Well, they shouldn't. I mean, if you are constructing it, if you constructed it out of multiple files and each partition maps to a file, then like, I don't know, maybe, you know,
Right.
but it'll cause issues.
But it does not
The-
vertically break.
No, it breaks them horizontally. Yeah. Any more questions at this point? Okay. Okay, so internally, we use map partitions all the time. So like for this index property on a data frame, this is, I didn't go back to check that this is still the implementation, but this was the implementation when we wrote this notebook. It's just a map partitions that gets the index from the meta? No, from the actual data frame. And we'll talk, so in this though, you'll see there's this meta argument. And this might not be the best way to segue into talking about meta, but that's what I'm gonna do. So Dask DataFrames and arrays have this attribute called _meta. And it allows them to know, I was saying that sometimes you need to tell it the D type, sometimes you need to tell it the chunks, like, especially when you're doing custom arrays. Meta is another thing like that. So meta is an empty version of the computed output, basically. And it allows Dask to keep track of what, here, let me take some water. Little cliffhanger. It allows Dask to keep track of what your output will look like so that you can chain together operations. So it keeps track of D type, so int, float, string, object, column name and order if you're column name if you're in data frame land, order of the chunks if you're in array land, the name of the whole object, and the type. So whether internally the partitions are pandas data frame, QDF data frame, in array, CuPy, others. So here's some metadata information. The information is stored in an empty object of the proper type. So you can, it's an underscore property, but you can look at it, and you can see that it's an empty data frame, and it tells you the names of the columns. So this is a real pandas data frame. It just has no rows. And this is how Dask knows what to render when you display a Dask object. So it goes and looks at that meta, and it uses those to make the column names, and then it knows that it's a pandas data frame. And if it had a name, I think that would show up somewhere. Okay. When you add items on a task graph, this is one of the things about meta that trips people up. When you add items on a task graph, so when you chain together operations, Dask tries to run the function on the meta before you call compute. So it does that right away, which might sound kind of weird, but it's how Dask knows if the shape of the object is going to be changing. So if there's a fundamental issue, it lets Dask fail really quickly, rather than waiting until you're like crunching through all of your actual data. So ddf.sum, for instance, you can see that instead of the column names being like, this was the data frame, right, where it has these 4 columns. But when you call ddf.sum, it collapses the columns and rotates it, and those become the index values, or the index keys, I guess. So that's how the Dask knows that that's what happens when you call .sum, because it runs .sum on the meta. Similarly, it knows that when you call .name.string.starts with, you're going to end up with a Boolean. So that's how Dask knows that what that dtype will be of the output is because it runs the function on the meta. And also, these became series instead of data frames for the same reason. So sometimes, okay, I have an example. First exercise, okay. It's pretty straightforward. It's just to see how you can make Dask fail really quickly by using starts with on a different column. So yeah, you can just type whatever you want, and then when you're ready to cheat, you can click on the little buttons. Okay. So yeah, so you should get an error message, right? Because if you choose a float or something and say that starts with A, that doesn't mean anything. So you get this helpful error message because of that meta. So it hasn't actually looked at your data at all, if you had real data. It's just running it on the empty object. All right, so sometimes when you're setting up custom operations, sometimes running the function on a miniature version doesn't produce a result that's right, or there is no mini version, there is no meta available. So you can provide a meta that will use as the output. So you're telling Dask that's what you're going to expect. So here in this map partitions, I'm telling it that this is going to be this meta. This is kind of like a specific style for writing the meta. You can also give it a pandas series, but it's saying the name is going to be greater than, and it's going to have, this is saying it's a pandas series, name's going to be greater than dtype bool. And then you'll see that here, dtype bool, name greater than. And you're telling Dask that when you do this, your Dask is trusting you to do it right, and there's no enforcement. So you might get an error like blowing up, or it might not be right, and like you just go call compute and you get something else, and Dask won't complain. Sometimes it'll trigger an error if you've chained a bunch of stuff after it and assumed that it was right, but if you just call compute, it'll just give you the dtype that it actually has when you call compute. Did you have a question?
Yeah. So the meta here is, it gives a series because you described like one column.
Yeah.
You had a list of those, you get an expectation of data frame.
Yeah, it's like there's some other syntax. I think it's like a dict or something. Like you can go look in the docs for that, I think. But you can also write like it doesn't have to be empty. You can also give it a little series that has some little values in it. But you just want it to be really small because it's going to be hit all the time. Okay? All right. So next we're going to talk about a different type. So we've been talking all about these embarrassingly parallel situations. But in this one we're going to talk about map overlap, which has to do with you're basically doing a per block operation, but there's a little bit of information that you need from the neighboring blocks. So some examples of that are convolving a filter across an image, rolling anything, like, and then searching for image motifs that might span the border of a block, evaluating a partial derivative. So this is like the image for that. So the way Dask array supports that is by creating a new array where each block is slightly expanded by the borders to include some values from its neighbors. There's like a cost associated with doing this copy, and there's communication of these chunks, but it lets you do these functions in a parallel manner. So the main API for those computations is map overlap, and map overlap is what's used map overlap is what's used internally to implement rolling. And it's very similar to map blocks, but it has the additional arguments of depth, boundary, and trim. So here's an example. We're going to be calculating the derivative. So here's the thing that we're going to be calculating the derivative of. So this is our little operation that's going to be operating on one chunk. We're going to say depth of 1, boundary of none. Wow, I wish we'd make a plot of that. Okay, in this case, each block shares one value with its neighbor. That's the depth of 1. And since we set boundary of none on the outer edges of the array, the first and last blocks are padded with the integers, or integer 0. Since we haven't specified trim, it's true by default, which means you're going to trim the boundary back off before you return the result. So otherwise, you'd have each of those still padded. So when you inspect the task graph, you see two mostly independent towers of tasks, but with some value sharing at the edges. So that's this get item here, where they're kind of like swapping back and forth between the two towers because they're sharing those borders. Okay, so the next exercise is to apply a Gaussian filter to an image, following the example from the SciPy docs. So you create a Dask array from a NumPy. First, we're going to create a Dask array from a NumPy array. And then you're going to use map overlap with this Gaussian filter and apply it to each block. Okay, I'm going to give you a minute and go get more water. Okay, solution time. Kind of gave a lot of it in the explanation. So you can set a depth and then a boundary, and you can plot the solution. So there's this crisp image, and then there's this like blurred image. And if you set the depth to a smaller value, you can see the edges of the blocks in the output image. So you can mess around with that if you want to develop some intuition. Okay, the next type of custom operations we're going to talk about is reduction. So that's supporting operations that reduce the dimensionality of the inputs. So things like mean, anything that aggregates. So internally, we use this on things like sum. And so this is the definition of the sum method, which is basically just a reduction of A, and applies this is normal numpy.sum. It's not called that because it might be like qpy.sum or some other whatever the type of the chunks is. And then so it's using sum on the on each chunk, and then it's also aggregating using numpy.sum. So here is Dask array.sum implemented as a custom reduction. So we have this array, and then we're doing numpy.sum on each chunk. Let me visualize it first. So we have each chunk, and then we're doing a sum on that chunk. That goes to an output. Then we sum again, and then we do the whole sum for all of the partial ones. Okay, so you can see in this exercise, you can see how that changes if you change the size of the chunks. Maybe to like, I don't know, you can make up your own numbers.
There is this assumption then that the reduction applies an associative operation across the
What does associative mean there?
That if you take two neighboring blocks, you aggregate them together
Oh, yeah.
first or after
Yeah.
some other pair, it changes nothing.
Yeah.
Okay.
Yeah. Right. So this isn't a good way to implement mean or something, right? Because if you take the mean of each chunk, and the chunks are different sizes, and then you take the mean of that, that's not right. Like, you don't get the right result because the size of the individual chunks matters. So instead you have to do things. So instead you would have to do like a count and a sum, and then at the end divide those by each other. I know that's not exactly what you were asking, but yeah.
Another question?
There's a cool question in that re-implementation of the sum. What is chunk?
Yes, that's literally just like copying and pasting Dask code. This is just saying, oh look, you can use reduction we use that internally to implement things. You can implement your own things. So that's like an internal Dask. There is a chunk module that stores a bunch of that. Yeah.
You can read that as NumPy.
That's what you were saying. Okay, now.
Yeah. So it's just so we can standardize across NumPy, CuPy, and the others.
Good question.
Any more questions? Great, making sense. Okay. Yeah, I think you can imagine what this will look like. But basically, if you make your chunks smaller, you'll have more of them. Surprise. And then you'll have to keep reducing, and you'll start seeing this tree structure shaking out. So how that tree structure is set up depends on this argument called split every. So in these, you can kind of see, maybe it's like super small, but you can see that each every 4 chunks comes together into a partial, and then that 4 comes together into another partial, and that's the default split every argument is 4. But you can also specify what you want your split every to be. So in this case, we're doing a partial. We can say on the 0 axis we want to split every 5, and on the 1 axis we want to split every 2. And here, this is not a custom operation. I'm just explaining the split every argument, I guess. But this is just the .sum method. So you can see that you have 10 now in each partial because you have 5 and 2. Okay. So you can mess around with different split every arguments and visualizing the task graph to see the impact. So here we're using 10 and 2, so we're going to have 20 in each partial. So that's something that can be really helpful to mess around with, especially when you're doing group by operations. It can be really helpful. You can use, so a side note, you can use reductions to calculate aggregations per block, even if you don't want to combine and aggregate the results of the block. So it's kind of like a little hacky, but if you specify a no-op, so this is a function that does nothing, right? It's just a lambda that takes an x and anything, and then just returns an x. If you specify that as your aggregator, then like you're just going to get the sum of each block, and it won't be reduced. It won't be reduced across the blocks. So okay, so in this notebook, I've introduced a bunch of different methods. Hopefully, it's like kind of clear how they're different from each other and when you'd want to use which one. But here, I've got a list in case you want to refer back to it. There's a couple that I didn't talk about as well that kind of have overlapping functionality. Probably the biggest one I didn't talk about is group by, which is kind of its own kettle of fish. But there's a lot of tweaking. If you do group by a lot and you have and you run into a lot of like out of memory issues or like other like issues with your task graph exploding, really dive into the keyword arguments because there's a lot of tweaking you can do to make that better. Okay, so the last section in this notebook is about customizing optimization. So Dask has a default optimization strategy for each collection type. So for arrays, bags, data frames, delayed. But you might have different needs. So often people, when they need to customize their optimization, what they end up doing is just turning off different optimizations. That ends up being what people do a lot if they run into issues. So this is just to say that there's these config values that you can set, like setting fuse.active to false. You can also construct your own custom optimization function and use it instead of the default. And there's good docs in the optimization docs on how exactly to go about that. But basically you construct a function that takes in the Dask task graph and the keys that you want out and does whatever you want to it, any optimization you want, and then returns the new task graph. And you can use that as your array, as your optimization function within a particular context, or you can set it globally. And you don't need to specify the optimization for all the collections. You can just do just array or whatever. Okay, next we're gonna have a break. 10 minutes? So we'll come back at 2:35. Cool.
All right, so we did a recap, then we went over some couple of custom operations. Now we're gonna dive a little bit more deeper into like the Dask distributed scheduler and then kind of poke around and then see how we can tweak things and stuff. This can be useful when you are debugging or something errored and then you wanna know what's going on and what happened. Just kind of like a disclaimer thing, certain things are going to be forced to be a way that might not be like the default, just to make it easier to explore, but we should have some fun. Right, so we talked earlier, Charles introduced us a little bit and talk about like what are the components of a Dask cluster, and just to recap that, we do have like a scheduler that sends tasks to workers for execution. And we do have the workers that are like the ones that do the work, and then they just compute stuff. And then like that's a component. And then we do have like the client, which submits the tasks to be executed. Now the client and the scheduler and workers don't have to be on the same network. We're gonna get to see like probably later on, like on an example where like your client could be in your laptop and then the scheduler and workers are in a machine remote somewhere, either an HPC cluster or like a cloud or somewhere else, in your grandma's house or who knows. Probably not, but all right. So couple of notes about like workers. I would say like there is an extra component to the scheduler. We're not gonna dive super deep into it, but like we have like a fourth component that's called the nanny. And by default, Dask workers are launched and managed by a separate nanny process, which basically allow us to, like if you do a client restart, then your workers will come up. And then sometimes they're like, you can restart workers automatically if they get above a certain memory limit and stuff. So then that's gonna be involved. That's usually what happens when you do like the local cluster that we saw earlier, like the client. It launches like all these nannies. We're not gonna dive deep into that just for the sake of like getting more into the workers and then be able to poke around. But it is possible, and then if you're interested on that, then there's plenty of documentation, and then we can like, or we can just play around a little bit if we got time at the end, which we probably will. So there was a question earlier about deploying Dask clusters. So in general, like when we are like on our laptops and single machines, we're gonna use managed clusters and stuff, but you can actually put together all the pieces of a cluster yourself and launch a scheduler and then launch a couple of workers and connect them to each other. So this is just, we're gonna do that like right now. But if you want to play on your terminal, you can actually do Dask scheduler, and then that will launch a scheduler. And then you can do Dask worker and connect it to the scheduler and then launch another one. That's like a fun thing to do if you want to. Now we're going to like run a couple of codes. So we have like these three different components that we have: the scheduler, the worker, the client. And here, what we're gonna do is basically create a worker, connect it to the scheduler, connect it to the client, and then do submit some computation. Like this is the part that is the submit. So just run this, and we should see a bunch of things happening here. I know it's red. I don't like it's red because every time I see red, I get scared. But this is just telling me what's going on. So it's we have the scheduler address, and then there's a dashboard, and there are a couple of workers. They are talking, and then it says waiting to connect, and this tells me that okay, threads, memory, and you can read a little bit more because this is in a context manager. Then as soon as it's finished the computation, then we'll start kind of closing each other and then kind of cleaning things up. So then you will see the below here, we have the result of the computation that we just did, that we just submit in this line. We printed the result, and then things start closing. So you'll see remove client, close stream, and all this stuff. Now, in general, we don't recommend like creating the clusters kind of like this way. Like we have clusters managers. This is more recommended. It's kind of like everything done on the back, and then you don't have to worry about this. The typical one that we use and see was the one that we saw before. It's a local cluster. We can create a cluster on our laptops. So we're going to do that. Now, I'm specifically going to tell it to use 4 workers and then 2 threads per worker. You can play with these values in your machines, depends on what you have. It's always interesting to see what happens. So we're launching a cluster. And we have this like nice little widgets that give me information about what is there. So it tells me there's a dashboard. Here are the 4 workers, the 8 threads, 2 threads per worker, some memory is using processes. And then you can like dive in, get info about the scheduler, and then we'll see like workers here. As you see, here is like the nanny process that we were talking about. And you can get into it and then, play with it. Part of the API is also that we can scale up and down the resources that we have. Like, so for example, we can do cluster scale and then say 10. So you'll see here, quickly change it, and then we says 10. We have like 10 workers now, 20 threads. We can also scale it down. So we can just go down, and it's like 2 and 4. And we also have access to the logs. So you can do like cluster get logs and then see what's going on. And they say, oh, remote worker, which just happened, and there were the other workers over there that we started earlier. You can go to the worker and then see some information. So far, we haven't done anything with this, so it's not telling me about other stuff, but you get the dashboard, like the dashboard, the worker dashboards and stuff. And then it's always good, like, just to close things down when you're not using them anymore, so then we can just go and close. We did have a question about, like, okay, when you have a big machine or like cloud or like a HPC cluster, you will have to kind of like do something to tell them like, hey, I have all this machine available and stuff. There are several projects in the Dask ecosystem to do for deploying clusters. And then we have like Dask Kubernetes, Dask Cloud Provider, Dask Yarn, Dask NumPy. I think there's plenty more. They're all like deployment packages of the way that you would kind of be able to tell like the HPC resource that, hey, I have all these resources to use, and then kind of how to tell it what to ask or not. And you can see here is a little bit of a syntax, but they all have more or less a pattern that you just get a kube cluster or a Fargate cluster, and then you just have the cluster instance and then pass the workers and stuff, and they all talk to each other. Yes?
Do all the clusters have similar, it seems like some of them have different shutdown methods and stuff like that. I mean, how much, is that true, or is it?
They all have a closed method.
Yeah.
Yeah, so they all have a closed method. That's part of like the cluster manager's spec.
Mm-hmm.
Yeah.
They have some different configs, right? Sometimes, or how you initialize the cluster and how to get it started.
Different. The dot is different. The core is for them. But yeah, they all have closed methods. The client has a close and a shutdown.
Oh.
Maybe that's what you're referring to.
So if you want to close down, you have something running, you want to close down a cluster, you can always do cluster that close.
Mm-hmm. Yeah. Now, aside of all the open source projects that we have, there are like companies like Coil that James and I work for, and then Saturn that you can actually, they will handle the deployment as a service offerings. It's like a disclaimer, James and I work for Coil, so then, well, we want you to use it, but then it's also a disclaimer. So there are plenty of open source projects that you can use. And at the end, we're going to play a little bit with the cold cluster, so then you can see what it looks like doing some computations in the cloud from your laptop to the cloud. So let's get into inspecting the cluster state, and then how we can get more familiarized with like the scheduler and worker processes, and then like track through what's happening in the cluster and all those stuff. So now we are going to create a local cluster, but instead of like leaving like completely open as we did before to use like nannies, we are forced to use our workers. So we can just dive in there and then play a little bit and then poke around. So we're doing that. This is, I think, I'm going to open it for you to see. So if you have the Dask Lab extension, then you can just click this button here. Technically, for some reason, it's not working on Charles' machine, but okay. So we're not going to do that. Oh, this one?
Yeah, there you go.
Okay, so we're over here. Okay, back into it. There we go. So you have access to the dashboard. That's one of the advantages of using a distributed cluster. So you can always click here. You have like multiple components to there and then different pages. But in general, by default, these are probably the 3 ones that you're going to start looking into it. And then see here, like on my bottom left, there is the memory, and then you'll see progress and task stream. So let's just do some stuff. A useful thing that we also have with the distributed scheduler is access to performance reports. So sometimes when you're like running computations and you want to know a little bit more of what's going on, and then see like the profile, like the flame graphs, and then what's happening, you can actually save that information into an HTML, and then you can share it with your coworkers or like your bosses or whoever, and then just try to figure out what's going on. And we have like a nice context manager, so you can just run your computation within there and then see what's going on. So if we just run this, we should see some action happening here. That was quick. We see like all this stuff. We're gonna go over into what the colors of the dashboard means, and then like what's happening in here on a later notebook. But the nice thing about this is it just run. So we should have here, where did it go? Save. We should have the, yeah. Is it? This one? Or, oh,
There's
over there.
this one. Sometimes. No.
No, it's not liking it. Well, we should have ended up with a file. I don't know why it's not there.
Yeah, go up there and see.
Here? We are at the top, so.
Are we not clicking, Charles?
Yeah, I don't know what's happening with it.
Come here.
It's your laptop, man. Talk to me.
Microsoft Edge, man.
Microsoft Edge on an Apple. I asked that.
Yeah. Yeah, I don't know.
Okay.
I don't know.
Well, we should have ended up with that. Let me see, can we? Yeah. Do you have? Yep.
Is there a way to tell them not to open it in Microsoft Edge?
I don't know if it's. Oh, I cannot open it on. Okay, so I guess I can't open it. Okay. Yeah, so it's somewhere in Finder. Do you have Finder? Well, you probably have a My Report HTML, so you can go and open the report. You can drag and drop it on the browser, and then you will see different parts where you can play around with it. There's some extra information about the duration of each part of the computations, and then what you've done there. But let's move along. So as we mentioned, like sometimes you will have a computation and then you will like have an error and then you want to know what happens. So it's very useful to be able to dive deep into the internals and see where that task erred and then where what's happening on that worker and then what's going on. So now I'm going to close this, guys, so you can all see better here. We have a function that we're going to map and then submit like to do some work, but we are explicitly making it fail a couple times. So then we can explore and then see what happens. So you see it here, and then, yeah, warning, compute fail. Yeah, I know. And then you get this error or no, and then we have like, I think it's around 4 or 5 tasks that fail. So we do have access to the scheduler. Not always you have access to the scheduler. There are ways of accessing it, but in this case, we do have access to the scheduler because it's in our laptops. So we're going to we get that information. It says 10 cores, 10 workers, 80 cores, 50 tasks, and we can see the scheduler address, then the time that it started, get the workers. So we have all these workers over here, and then see what we've been doing. I'm curious now, why do we have that many workers when we told it to have 4? Well, and we can inspect like the worker states and then see kind of what's going on. So now we were in the scheduler, now we're like diving into a worker. So we just grab one, then go get the address of that worker. The status says it's running, it's up. See the amount of threads, it's 8. Is executing anything? No, we're not running stuff at the moment. And you can get some metrics. This is usually very useful. It tells us like the task count, like in memory, there are like 5 tasks in memory. There's some information about the bandwidth, if there was a spill, bytes, and then you can see like plenty other stuff over here that can be useful to understand better your problem. So, and we do have like this is a good thing. So the scheduler and worker like communicate to each other. So you can see when was the worker state, like when was last seen. So then you get like a time, but this is constantly happening. So there is like a check-in, like a ping kind of situation that you're saying, hey, are you there? Yes, I'm here. And then it's like, that's continuously going on. And then you're collecting like all these metrics and stuff, and then sending tasks to each other and so on and so forth. So we get to see the tasks. So we have all tons of tasks here. We just did that computation that was double. So you see here, all the tasks will have like this name that it starts double, and then it has like a long number that to make it unique. All of these ones are unique. And it tells me if they are in memory or they erred. And then there are like other states for the task. Like there is some docs down here at some point that you can see what are all the possibilities. It could be processing, waiting, queued, and that will give you information about what's going on. So we're just like looking at a little bit more into one of those. So then we get, this is just one specific key. The state of that key in this case is memory. I could have picked another one that could have been error. And then we can check like, okay, what are the workers who have this task in memory? So this comes in handy when like you're looking for the ones that had error tasks or like they were error, and then you want to see, okay, who's the worker that has that? And then you can get the address, the location of that worker, and then probably dive in there and then take a look. There are like some extra info that you have. If you type like, let's see, like we get the type, and then we have the retries too. Sometimes you can see like how many times this task can automatically be retried on failure. So you can get that information. This one wasn't retried. And there are like plenty other things that you can check on the state. So if you usually do, then like do dot and then press tab, you will see all the things related to that. Are there dependencies to these stacks? What error on, and then exceptions and plenty other stuff. So you can keep like running cells and then check any other stuff. So let's do an exercise. We'll take like around 5 minutes, 5-6 minutes. And let's try to see if we can get what are the keys for this task which fail? So let's try to find the ones that fail, and how many tasks successfully run on each worker. So let's just take 5 minutes. What time is it? It's 56, so then let's do a 3:01, and then we get back to it. Also, feel free to ask any questions, and then go. There we go. Okay, what are we? Okay, we are on time. So we're gonna see one of the solutions here. Okay, so we can check on the scheduler that we have the task and the items, and we can check if the state was aired. So we can just do a less comprehension here and then check that. We should have 4, yep, and we do have over there. And some kind of similar thing we'll do if we want to see how many tasks successfully run on each worker. So it's a little bit more convoluted and complicated. There are like 2 ways of going about this. You can kind of like create a counter and then check if it was aired and then continue, and if it didn't or was in memory or who has it, then you can do a +1. I think this one is a little bit more complicated. I like this one because it's shorter. It's easier. But before we saw this, right? Like I'm going to type it over here. But we have the, I think it was task date metrics. And what I'm doing. No, okay, so it wasn't that. I think it was. Yeah, okay. We saw it before up somewhere over here when we're looking into the metrics. Yeah, over here, worker state was, thanks, yeah. And we see this like memory, and then there was 5. That's like the numbers that are in memory that successfully run. So we can just count those and go over that. So this will give us like, whether we run this, we get a little bit more information because we're creating there and then we charge. But here with the counter, we just get, each worker gets, okay, 5, 4, 4, 4. And then the ones that have failed ones are the ones that have 4 over there. Right, so in addition to see like what's happening on the scheduler, we can actually get more like into the workers themselves. So we can just access the workers. So we have all of these ones here. So let's just pick one. We'll go over, again, like we can get the address, we can see the worker state, and then how many number of tasks are currently computing in there. So we have nothing running now, so, but we can see how many, the total number of tasks that were processed on that worker. So in this case was 30. We get the number of threads, the executor, in case you want it, what are the keys that are currently in memory in that worker. And then this is like worker data is where the worker itself stores the task results. So you'll see this weird thing that is like a buffer LRU kind of looking like thingy. Don't need to get too much into, but if you're curious about it, that's where things live on the worker before it sends them to the scheduler and client and stuff. And we can see like in the worker where the results get stored on each of those. So we can dive in there and then we can see how many they are. So we see like, I think this is like probably the name, and then we see where they are. All right, so far we've been like accessing things on we have access to the scheduler. What happens if our scheduler wasn't on my local laptop and then I need to tell them, hey, give me the name of the worker, so give me stuff, and your clusters, and your scheduler is in a cluster, for example, in the cloud. You can still request for all this information, ask it. There's kind of like you need to do something a little bit different. You need to run things on the scheduler or run things on the workers to be able to get that. So for that, we use usually client run or then client run on a scheduler. And the way that this works, it's kind of neat. So we create a function, for example, in this case, get worker name. And if you provide Dask worker as a variable, then that will return, like for all the Dask workers, the name, for example, in this case. So if we run that one, you'll see, oh, for all of the Dask workers, then you get, this is the name. So really, really original names, 0, 1, 4, etc. And if we want to see, for example, get more info from the scheduler, and the scheduler will be like somewhere else, you can, instead of doing Dask worker, you do Dask scheduler, and then you can get access to that. And then, for example, this one was when we were checking where the error tasks were, so we can just check that. And we'll do run on a scheduler. In this case, it's the exact same thing that we were doing before, but if the scheduler wasn't on my laptop, then this is how we will get that information. So we're gonna close these ones now, and then now we're going to dive deeper into do things, like sometimes we need to do things that are not like implemented, and there are ways, like a Dask distributor has like a Dask plugin system to extend the abilities and the capabilities of the scheduler as well as the workers. So you can write your own kind of class that needs to follow certain instructions, and then you can actually extend what you need to do with the scheduler and the worker. So, yeah.
When you did client close, do you need to do client close? If you use custom close, does it automatically close the client, or is it sometimes leave?
No, if like, I think like if you do client shutdown, that will close the cluster. But like if you do client close, that won't close the cluster.
But if you do cluster close, does it close the
No.
what's the cluster?
Cluster close wouldn't close the client, would it?
So the cluster will close if you call cluster at close, but the client will just sit there. Yeah, just because you don't know, the cluster doesn't know what the client is. Yeah.
It doesn't know if there are multiple clients connected to the same cluster.
Oh, okay, yeah.
So it doesn't like just shut down all the
Okay.
clients also.
All right, so let's see how we will like kind of write some plugins and then things that we could do to extend it. So as we said, like we have like kind of two different components that we have, like the scheduler, and then we can extend the capabilities with custom code. And for that, it's like enables you to run like custom code when certain events on the scheduler happen. So when it starts, it stops, gets restarted, there are connects or disconnects, you can get info there. Then when workers get in and out of the cluster, or new task enters the scheduler, or task changes states. It goes from processing to memory, or maybe error or something like that. And then the worker plugin system is kind of, it's a little bit more reduced. It's like not that many crazy things, but you can still add custom codes and then check when it happens, when, for example, worker starts or stops, or it releases the task, or the task changes states. So let's just check quickly a little bit of what the life cycle of the scheduler plugin in is, like the things that you would kind of like need to implement to be able to extend that, or parts that you can add to it. So we'll see that the life cycle of a scheduler plugin will have like all this kind of methods over here that we says that, oh, when it restarts or starts or transition, or there's an update on the graph, then in there you can kind of like add code or modify those methods and then see what's going on. And then for the worker plugin, those are like much simpler. There's like 3 things, then you can kind of add code into there, which is like setup, turn in, and transition. So here is a simple example of what a scheduler plugin will look. So the way that we construct these ones are, you create a class that will have as, it will kind of be using or inheriting the scheduler plugin class. You got, in this case, what we're doing is keeps running a count of the total number of completed tasks. So we just kind of like have a counter variable here, and then we say transition. In this method, what we do is, if it starts in processing, so we have a task that is processing and finishing memory, that means that, oh, completed, so then we count 1. And you can read a little bit more about the task states. There's like some docs here. We're gonna be moving around processing and memory today, so. And then you count, and then if the scheduler restarts, then you cannot set the count back to 0. So you can run that. That won't do nothing. It's just creating the class. Now, how do we use this, guys? So you created your class. Now you have you will have a cluster. You got, in this case, let's just do the local cluster like as we were doing. You will instantiate the class, and then you will add the plugin. You will add it to the plugin. So you will add that instance to the plugin. So let's just run that. Now, here, you will have access to this counter stuff. So if we do counter send task, we'll say 0, because we haven't run anything. Now, I'm just going to do, oops. Just send me down here. So if we run something, let's just map a +1 function, and then on the range, so we'll see something happen here. We get these futures. We didn't talk much about futures, but this is something else that you have. If you notice when you run this cell, it runs really quickly, but it doesn't block your cell. So it's like async running in the cluster. But then now we can check the counter end task because this plugin is added to the schedulers, and I can check, and then I have 27 tasks. Now, if we restart the client, then we'll say restart, and then it's restarting. And then because these are nannies, then all my worker restarts get up in there. And then we can see now that the counter is back to 0. So we're gonna close this one now. We're not gonna use much. There are plenty of other plugins that are very useful, and we found that, okay, many people were using it or needed something like that, so were added. They're part of distributed, so you can check some. There are plenty that are useful. Environment, upload file, upload directory, allows you to kind of upload a directory, and then you can do something with it. Or upload a file, it could be a Python wheel, and then you can run just that package there. There's a pip install and a package install and conda install, so you can extend those. We're not gonna dive into them. If you just want to check, oops, I did. Something for some syntax error. Oh, this space. That's finicky. I don't like that. Well, but this one is just, you see here, we have this setup, and then it's just kind of updating environment variables. And package install is another one that it's kind of like a class that we use to extend the, not to extend, it's pip install, depends on package install and conda install. And you can take a look at them. I like maybe one more useful is upload directory, this one. They get a little bit more, this one is a nanny plugin, but you can get the idea that there are a couple of, there's a setup method over here, and you can have other stuff happen. You can take a look, play around. We're gonna take now 10 to 15 or 10 to 12, we'll see how we go, minutes. You're gonna implement your own scheduler plugin, which is going to keep tracks of how long each task takes to run. So there is some code in here, not too much, but it's basically, we are gonna be working on the plugin here. So let's say sometimes if we have some questions, let's move around or work with your peers, and then let's try to get create a plugin. All right, we'll do 10 minutes? 10 minutes? All right, so how are we doing? Did we get some code, some errors? Most likely errors, it's hard. But yeah, let's I'm gonna show the solution, and then we're gonna walk through a little bit. So here we go, bunch of code. This is the plugin component part that we're looking. So basically what we want is like when a task starts processing, we want to start a clock, and then when it finish, and the word finish here is a little confusing, but when it's in memory, then we want to stop the clock. So the way that we kind of check for that is we do have the transition method here, and then we check like if finish, and this is tricky, I know it's confusing, but if finish is processing, means like it was somewhere there, I don't queue or waiting, and then now moves to processing, then we start the clock, and we save the key in there in some start times, and then when it goes from processing to memory, then we clock again, and then we just like have like the task durations will be like finish minus or end minus stop times minus start times, and yeah, we can play a little bit with this. So we are going to like create a cluster, then register there, do some computation, and then see what the plugin the task durations are. So if we just run that, it'll take a little bit, and then we'll get all this. So we get like this random sample, and then we get here like how long it took, and then you have like all these things. You see here like we're doing a random, like it's a random array, and then we're doing like a transpose and mean, and then a sum, and you'll see like read chunk, merge, and all this stuff. Sometimes, yeah, it can be useful to visualize these things, like the same way that we were visualizing like before the task graphs, but here like you will get that access. So if we want to like plot that, then we can just get the items, and you get like the key and the value, and then we do some sort of histogram, and then we can just plot that nicely and then see how long these ones were, like the counts of. So some on 100 milliseconds, they were like around, what is it, like bunch of tasks, and then we get 10, 100 tasks and stuff. So as a summary, like we just went over on how to dive deeper into the scheduler and into the workers, and then poke around, and then also being able to kind of explore the task states and then see what happens with that, and also being able to go from how to extend the capabilities of the scheduler or workers, and then how you can use that machinery for your own purpose to kind of get extra info that you might want. So now I'm going to hand it over. Well, we should, yeah, question, sorry.
I'm curious, and maybe I missed this, maybe you already went over this, but when you created your class object for the plugin, you have that sub-method kind of transitions in there. It's never called directly by the code. Is that just underlying Dask structure? Oh, that's what I figured.
Yeah, so like when we went, I think it was up in here, we're seeing like the life cycle of the scheduler. Yeah, so that method would kind of get called like every like X amount of time, kind of like pinging in there and then checking. Yeah, so that would be, yeah. Any other questions? Great question, by the way.
Okay, so how are folks doing? I'm seeing some thumbs up, probably some thumbs sideways. Okay, I'm gonna go ahead and get started here at least. So yeah, we're going to talk about, we're going to look at one particular workflow. It's a Dask DataFrame workflow. Does some ETL things. We're going to read in a data set and do some sort of common operations that people do when playing with tabular data. We're going to start with some code that looks perfectly reasonable but doesn't happen to be very performant. We're going to like run this a few times. We're going to encode some best practices, change things a little bit slightly, and in the end, we're going to have a performant thing. So that's kind of the goal for this notebook, is to encode some best practices. We're going to see how we can use the dashboard here effectively to kind of diagnose performance issues as well.
Do you want like extra questions in this section?
Yeah, that sounds great. We have time, so feel free to have extra questions. So the data set we're going to be using here is the Uber Lyft taxi data set. So it's a few things to note about it. We're using a subsample, by the way. Here's a link if you want to like get more information about this data set or the schema. But the subset we're using, it's a CSV data set. It's approximately 115 gigabytes when loaded into memory. So that's why we're using a cluster here. I'm not using Naty's laptop because that will not fit into memory on Naty's laptop. Here's the particular bucket in S3 it happens to be located in, and it's in US East 2, that's the region. So like I said, the first thing we're going to do is spin up this coiled cluster here. So what's happening here is, actually you earlier asked about package environments. Yeah, so what this is doing is automatically syncing our environment that we have locally, remotely to the coiled cluster. So here we don't have to maintain any Docker images or anything like that. That will automatically be built for us. So the remote and local things will have the same versions of NumPy, Dask, all of that good stuff installed. Also, like, this is now getting into a minor coiled sales pitch, which I'm going to keep doing, but just know that in the previous notebook, we talked about a lot of the other deployment technologies, things like Dask Kubernetes, things like Dask Gateway. Those will also work just fine for this. Coiled's it's a smoother experience. I don't have to do the Docker images, for example, but just know those other things perfectly fine to use as well. And yeah, so we can go over here and we can see this notebook spinning up. Here's the notebook here from Naty. We'll see this typically takes 1 to 2 minutes for my instance to provision, for the software environment to be downloaded onto the cluster.
Is anyone still getting those timeout errors? Everyone got on the AT patch network? Untickling sounds like it's pretty fixed.
Yeah. How'd you create your environment? Did you use the conda environment file or the?
No, I just created a break one.
Okay. You might not have you might not have the right versions of packages installed, is what I'm guessing, without looking at the traceback, is what I'm saying. Oh, you did? Okay. Well, then I'm not sure. I would need to look closer. I'm gonna like gloss over that for now, but we can take a break a little bit. Sure. Yeah. So here we can see things are booting up. Right now, I'm currently, this software environment that got scraped locally, it's getting pushed up. It is getting installed on the cluster right now. I should also say, I asked for 20 workers. That's the size of the cluster. And then I also, this is maybe a best practice, I asked for it to be in region US East 2. That's because that's where the data set happens to be located. If I was analyzing something that was in US West 1, I'd want my compute to be spun up there to minimize any sort of transfer costs. Okay, looks like my cluster is here. So yeah, we are now connected. So from this point on, all the code is just general Dask looking stuff. The only like cluster part, in this case it was coiled, but if we were using Dask Kubernetes or something else, it's really just spinning up that cluster at the top. Everything else is totally agnostic from whatever you're using to deploy your system. So here I'm printing the client repr. This looks exactly like when we were printing the local cluster repr, just the dashboard is like somewhere on the internet instead of on my local machine. So I'm going to go ahead and fire up the Jupyter Lab extension dashboard. There we go. So yeah, we should get our dashboard plots here. So what we're going to do is actually start working on this workflow. So the first thing I'm going to do is read in this CSV data set. So Dask has a read CSV method. Here I'm pointing to the data set here. There's this thing that I'm totally going to gloss over here where I'm saying, oh, I'll circle back to it, but for now I'm totally going to gloss over and say this D type needs to be a category. Later on, we'll talk, yeah, I'll get to it in a second. Later on, we will talk about D type inference in a minute. And yeah, there's a question?
I got an OS here about trying to open up that data set.
Yeah, I'm getting a resolve no files on the S3.
Interesting. Okay.
Can you probably add the unknown equal to?
Ah, cool. What if people do this? Does that help?
Oh, because you have the credentials locally.
No, it should be a public data set.
But like for that.
Perfect. Okay. Let's.
If someone is curious about
Yeah,
that,
it's
then we can chat.
it's good, Naty. Cool. So yeah, that took 15 seconds. That wasn't actually loading in the full data set. That was like inspecting the data set, looking at metadata, trying to get the meta object Julia was referring to earlier, get D types, get column names, things like that. I now have that information. Don't have the actual data, but I have column names. I have D types here. We can see the data set has lots of object types here. It's got some floats. I can see this is taxi data, so I can see how long the trips were in miles, how long both temporally and in distance, were there any tolls, sales tax, things like that. So yeah, we can do all sort of all of the normal Dask DataFrames here to kind of play around. I'm now going to choose to do some specific things that are kind of representative of an ETL workload. So first thing we're going to do is I see things that have date time in the column name, but they're being stored as objects. They're not being like actually stored as, you know, datetime 64 or whatever. So I'm going to convert those. I'm going to move this over so we can get more code for now. So yeah, I'm going to do data framey things. I'm going to take 2 of the datetime columns, which are currently just being stored like as strings that look like datetimes, and convert them to actual datetime objects. Yeah, question?
Object is just like a synonym for string. I'm not.
Strings are objects. Objects is anything in Python. So if you have a class, yeah, so yes.
Is there, like, other than the fact that you know because you've seen this data set before, how do you know what type these objects actually are?
Oh, it's an object D type. It's, yeah.
Pandas uses object types to represent strings. Like anytime you have a string in pandas, it's going to be
An object.
default, it's going to be an object.
Okay.
Does that answer your question?
Yeah, I think so.
Okay. Yeah, so I'm going to convert some columns to date time. I'm going to then take those date time columns and do some feature engineering with them. I'm going to put them into their own columns. This is more just a formatting thing, but this is a thing people like to do. They like to have things that say pick up month, pick up hour, things like that. That's a little more palatable than an actual date time object. I'm then going to drop some of the columns that I no longer need because I've moved them into other columns. So I'm going to run this. That was really fast. That was just setting up the task graph. So the other sort of thing I'm going to do here is do some normalization. This is another really common task when working with working with any data. So I'm going to do some NaN handling here. There's this airport fee column. It has some NaN values in it. I'm going to replace those with 0 and just say that is no fee. I'm then going to remove some outliers. So I'm going to compute some quantiles, and I'm going to select trips in my data frame. I'm going to look at just the subset where we're sort of within that lower and upper bound here. Keep in mind the details of this aren't super important. This just should look and feel like normal things you might see when working with data frames. The last thing I'm going to do is there's this column called HVFHS license number. Turns out that this, if you look at the schema, actually corresponds to was this an Uber ride? Was this a Lyft ride? You know, I'm going to then convert that column into the weird hashes it has there to be oh, this was an Uber ride, this was a Lyft ride, etc. I'm going to use this map and apply that. Then I'm going to remove the old column because now I have this service names column, which is I can understand more. I know if it's what the service provider was. Again, this is just setting up the task graph here. It's not actually doing the computation. But let's do some computations. So I'm now going to, now that things are kind of cleaned up and we've massaged the columns in a way that the data is now easier to work with, let's compute some things. Throughout the notebook, we're now going to just repeat a bunch of this stuff, except we're going to encode some best practices. So whenever I say we do all the setup stuff, the stuff I just did, where all of the changing of columns and things like that, that's the sort of setup stuff. We're just going to run through the same exact code again. So here we're going to calculate what's the average tip fraction. So here we have our tips column, and we can say if it's greater than 0, now we have a binary thing. It's either 1 or 0, and we can then compute the mean of that to get the average frequency of tips. So now we see this happening on the cluster itself. We see a bunch of things flying by here on the task stream, all these tasks. We see things going into worker memory here. We see the actual progress of the individual tasks in the task graph. So they're color-coded up here. We can see a bunch of things called a sign. That's these blue tasks here. There's some tiny green things you can't really see here. Those are the quantiles. This is just going through, doing that read CSV call, and doing that data manipulation. We're computing those outliers. We're renaming columns. We're selecting subsets of our data frame. And we're going to let this happen. Okay, so this means about 16% of the time, someone tips. And that took about a minute here. I'm now going to do these two back to back. The computations here are just group bys. So we're going to take our or group by reductions. We're going to take our data frame. We're going to select subsets here. In the data frame, we're only going to look at things where there is a non-zero tip. So if the tip's greater than 0, we're going to group by the service name. So we're going to look at the data set for just things where people have tipped. We're then going to group by, is it an Uber ride? Is it a Lyft ride, etc. We're then going to calculate, in this cell, we're going to compute the sum of the tips for that group. And then here, we're going to do the mean. So a very similar computation. Yeah, question? For memory, yes. Yeah, so you can set memory limits. For CPU limits, you can set the size of the thread pool on the worker. This relies on your tasks that are running there to themselves not do other things. Yeah.
Okay.
Hopefully that answers the question. Yeah.
I guess similar question. Did Coil decide what the instance size should be, or was that like a default setting?
Yeah, I use the default setting. It's about a laptop. David, do you know the default instance? I think it's like
M6i X large.
yeah, on AWS, that's the default instance. It's about a laptop. So this cluster is about 20 laptops. You can choose whatever instance you want here. Yeah.
The biggest value from using Flow in this context is that it's data proximate, so it's all in the left, right? So it's like, that's the main thing that we're getting from using the Flow cluster.
Yeah.
The computation happens next to the data.
Yeah, if I was to run this on my laptop, I'd have a bad time for many reasons because the data set's just way, way, way bigger than my laptop. Also, the data transfers. Yeah, transferring all that data from AWS to my laptop is just going to be slow. And then I guess we're at a conference too. So we're all sharing internet, so it's going to be extra bad. Yeah. Okay, it looks like all these computations finished. And we can see the results. The actual numerical results here aren't super important. The point is we did some data framey things that are very common to do. Doing group bys are really common in analyses. And the thing that's important here are the times. So the first computation, well, they all took about a minute. So that's like the starting point. Let's log that minute in our head, and let's see what we can do to that minute runtime as we work through the notebook. I'm rounding up here, 50 seconds to a minute. Okay, so let's start talking about best practices. So the first thing to know here is that I was kind of talking over that, so I apologize. I'm going to rerun this. So when we were running these computations, they were you would see very similar things happening in the task stream for all of you would see something that looks like this. You would see a bunch of blue assigns that are happening here with a bunch of little green things inside of them. And then you would see the exact, and then some other stuff is going to happen. But you would see this step in all of the computations. And this step is actually taking a while. We're sitting here and I'm talking for 20 seconds and blue things are passing by on the task stream. That's because whenever we do Dask computations, they are just building up this task graph for us lazily, and when you call compute, it computes whatever the graph is. So here, although it looks like we're just computing get the tips column, find the rows where it's bigger than 0, and then compute the mean of that thing, that is what we're doing, but that's just the end of the computation here. Because remember how we got DDF? We had to read in our data set with the read CSV call. We had to change all the columns. We had to do all that stuff. So all that pre-processing stuff that happened for DDF happens here, and it happens here, and it happens here. So that can be inefficient. So that's sort of the take-home point of this best practice, which is to persist when possible. So it's really common for people to do exactly what we did here. I'm going to load in my data. I'm going to play with it a little bit. I'm going to do a bunch of repeat computations on it. I'm going to do some analysis on this thing. I'm going to explore. I'm going to compute the mean. I'm going to compute some other statistics. I'm going to do some other things with the data. I'm going to make a plot. So what we recommend is, when possible, persist your data set. Once you get to that point where you have things in a analysis-ready state, and I'm going to do a bunch of computations on the same data set, go ahead and persist that into memory. So I ran these cells back to back really quickly. Notice the first one here happened instantaneously. And now I'm seeing all those blue things that I was happening before on the task stream when I was running read CSV and doing all those manipulations to the data set. Those are now happening in the background. This is going to block, this wait function in distributed is going to block until that's all done in the background. But right now in the background, we're loading this data set into my cluster's distributed memory. Yeah, there was a question?
Is that, okay, that's loading it into the worker's memory?
Yes. Yeah, exactly. So all those tasks, it's basically saying, don't run them whenever up here when I was just doing a compute call. It was running exactly what I told it to do and then stopping and clearing up everything on the workers. Here what we're doing is we're getting references. We're saying, go ahead and do that and then keep the results on the cluster and give me pointers to that data. I'm going to use that later. I'm going to do a bunch of computations on this.
The data is still distributed across the
Yeah, so I can see it here. If I go to my worker memory, I can see here the managed memory on this particular worker is 1.4 gigabytes. That's 1.4 gigabytes of this persisted data frame on that worker, and each of them have about that. So, yeah, question.
To be sure, when you say persistence here, that's in memory though.
This is in-memory persistence. Yep, exactly. So on the worker processes that, and here happen to be on AWS, those workers now have this data loaded into memory there.
You might get to this later, and it was already a question related to this. Is there a way to persist this more permanently so that if the kernel gets killed, the worker gets shut down, and you want to reboot up, like at the end of the
Yeah.
you have to shut everything down, you've done all of valuable computation.
Yeah, so what I would do is just save it to an S3 bucket, or wherever you store your data. I would just,
To get the state written to another CSV file that has
yeah, so like for example, you're saying like, my data set is now, a common thing that happens is like one person or a team does this pre-processing. There's a data engineering team. And then they would do something like to CSV, like wherever you store your data. And then other data analysts and scientists will then consume that later, that data set. I think that's answering your question, but let me know if it doesn't.
It's difficult to see how the syntax is quite new. So
Yeah.
a lot of interpreting.
Sure, persist here is memory.
Write this down and get the CSV that is back end of the next thing. But that works. That works.
Yeah. Yeah. Cool, okay, so note that this took 50 seconds to load this data set into my cluster's memory. If I go up here and, well, these were like a minute, right? So that means each of these computations we were doing before, like the tip part and the group by part is a smaller fraction, right? Of the actual computation. Most of what I was doing was actually loading in my data set and doing that pre-processing. So now I've done that once. So when I do my computations down here, again, these are just the same lines of code as before. I'm just now using my persisted data frame. So I'm now going to run all of these. And what we'll see is we don't see all that blue stuff happening anymore, all those read CSV calls, because that's already happened. We're basically starting from that point for these computations and just doing the remainder of what's specified in the cell. So in here, we're just computing the means of these tips, or of the fraction of the tips. And notice now these computations, this is 7 seconds, this is 4 seconds, this is 7 seconds. This is like the diff between this 50 seconds to do the data pre-processing and the previous minute that we had. So the best practice here is when you can, persist into memory. If when you would want to persist in memory is if you're going to be doing repeat computations. If you're only doing a single pass through the data, there's no need to persist. Like, don't worry about it. This is just for repeat computations. This is also if your cluster can handle the data set in its memory. So that's sort of a requirement here, because as was mentioned before, we are loading the data set into the worker memory, so your workers need to be able to accommodate your full data set. There were a few questions. One over here.
Yeah, so if say another client connects to the same cluster, are they able to get a reference to that persisted data?
Yes.
How do you do that?
So you can, let's circle back. You can do that, yes. There's a slightly different API. There's like a notion of data sets, which is more of a shared thing there. Yeah. Were there other questions? I thought I saw hands here, but maybe not. Zach?
Yeah, I was gonna ask, are there any considerations for like cloud instances?
Yes.
In this case, would you just recommend not using cloud instances?
It is fault tolerant, yeah. So if, great question. So there's a like little keyword we can say when we spun up our coiled cluster, like use spot instances, and it would then use spot instances. And is everyone familiar with spot instances? It just means they're a lot, this is a cloud thing, they're a lot cheaper than normal persistent instances. And what you get for that cheapness is sometimes they go away. So what will happen here in this context is it'll probably be up for most of the computation. Maybe one worker dies. That worker will quickly try to, in the window it has to close down, say, hey, scheduler, I have these, this is the data I have. Please send this to other workers. And if it can do that, then great, you're good. If it can do that in the time before it dies, it's crisis averted. If it doesn't happen, later on when you do your computations, it'll say, oh, I don't have this key. Let me go ahead and recompute that. So yeah. Mm-hmm.
So does workers actually subscribe to this signal that says you're about to be shut down, or you said that there were things that I think with spot instances there, whatever meta schedule is there will let them know when the 30 seconds you're about to, your VM is about to be.
Yeah, so AWS will tell the instance that it's
Yeah, but so
going to be
the Dask workers listening for this and will try to shut down gracefully. Always.
Coil is doing that.
Oh, Quad. And this works because this is AWS specific, right? Or scheduler specific. So if you go to like an HPC system where it's Slurm running, they have a different way of doing this. So what's the integration?
Dask will look for like closing down signals, and if it gets one, it'll do a best attempt to have a graceful closing before it can. Sometimes that doesn't happen. Sometimes it doesn't get the signal. Sometimes it can't do the graceful shutting down. Yeah.
I said listening to this AWS signal in the coil thing, but we have a blog post that says what we get from time. You can read it and do it yourself in a different system if you want to.
Yeah. Okay, so great questions. So just circling back to the point here, persist when it makes sense and when you can.
Can I say one more thing?
Yeah.
Like the task graph is still there, so it still knows how to go and read that data, even if a worker gets killed. And so if it doesn't find a worker that has the data, it'll go redo that part.
Yeah, so it's robust enough that
Yeah.
it doesn't even know what happened, but it will notice a worker
Yeah,
died
it's
and
like-
it will relaunch it and repopulate the data.
Yeah.
Okay. The second sort of best practice we're going to talk about here is when we're doing these repeat computations, you can actually compute multiple things at the same time. So here, these are the same lines as before. I'm just assigning them to variables. So here's that tip fraction. Here's the group by sum. Here's the group by mean. So I'll go ahead and run that cell. Again, that's just setting up the graph. Before, what I was doing is running these in 3 different cells separately. However, there are similar things going on in these computations. In particular, if we look at the group by sum and the group by mean, everything except just at the very end where I call sum or mean is exactly the same. All the group by stuff, the selecting of the tips column, all that's the exact same. So when you run these separately in different cells, you're redoing that computation again. You're redoing all the group by logic multiple times. So what you can do is use this top level Dask compute function to compute multiple things. And what Dask will do is it will inspect these graphs, and if there are any sort of shared intermediate dependencies, it'll compute it once and then share that results with the rest of the downstream things, which may be different. So in this case, the trip fraction and the group bys don't have a lot in common, but the 2 group bys are very similar. So we're only going to do that group by once, and then we're going to split after that into the 2 separate things. In this particular case, it just means we're going to then use that result and call sum on it, and for the other one, we're going to call mean for the 2 different group bys. So these are all running in the background. Yeah. Yeah, so that took a lot longer than I was expecting, and the reason is one of these workers died. And notice we still got our result. It just took a little bit longer. So notice this worker here, the bytes stored on that worker are way smaller. I think this worker died and has come back. But notice I still got an answer. It just took longer than expected. So I'm going to try and rerun this now and see if it's faster. Oh, that didn't do it. Oh, that's right. Now these are not, yeah. Yeah. No, that's fine. So anyways, this would have been shorter had I not had a worker die. I'm going to now retry it again and see if it's shorter. Great. Now that took 15 seconds and not 50. I should have said that earlier. It took 50 seconds before because the one worker, it had to redo the computations that were stored on that. But now we're down to 15 seconds. So if you add up these previous numbers, this should be faster because some of the group by operations we only had to do once. So got a little sidetracked there, but this was nice because I did not do that on purpose, but I got to unintentionally address a question that was asked. Okay, great. Yeah.
Back to the question about Spot, I just looked this up. For example, Dask Classifier, an open source cluster manager, does a similar thing. Like that'll handle Spot interruptions. It looks like it does. I didn't try it gracefully, but it's kind of up to the cluster manager. Many will do good things for you.
Yeah. Okay, great. So, yeah, any other questions at this point? Yeah.
So like a global setting to always use Dask.computer to try to see whether that part that you're trying now is already.
There's not, no. No. The next thing, sorry, any other questions? Okay. Next thing is to store data efficiently. So, so far we've been using CSV. We've been using read CSV because our data set is stored in CSV. And this is fine, it works. However, oftentimes things like I/O will be the bottleneck here. So in workloads, for example, earlier, like of the minute that it took to do the computation, basically 50 seconds of that was loading data in and manipulating it. So the next best practice here is to store your data efficiently. So when working with tabular data, we recommend using Parquet. So Parquet is it's a really popular file format for tabular data, and it's very efficient. It handles random access. Importantly, metadata storage, that's another big thing about Parquet as a file format, and other things like encoding and compression well. So what we're going to do is we're now going to start back from the beginning of our computation, but we're going to use Parquet data instead of CSV data. So we happen to have a second version of this data set that's saved in Parquet, also in S3. And so, I guess for folks who ran into issues, add the same storage options to this call. So just copy that from before and do that here. So this is the call I had before. I've now just commented that out, and I'm replacing it with read Parquet. Again, same data set, different file format. That was actually a lot faster before. I'm actually blanking on what it was, but this step itself, just to construct the task graph, was much smaller because Parquet handles its metadata more efficiently than CSV does. Another thing I didn't have to do was I didn't have to specify this dtype equals. So sometimes when working with CSV data sets, you might have 1,000 files in some directory somewhere that are all CSV files, and depending on how carefully the person who produced that data set wrote things out, there might be mismatches between the files. So for example, if before, when I was doing this read CSV call, Dask will do its best job to try and infer those data types, but it can't do that perfectly without cycling through the full data set, which it can be really expensive in some cases. So I said, hey, I actually know this thing's a category D type, because most of the files had a category, or had a string, had a flag basically, but some had nuns in them. And so there is this, if you try to read in the data set without that, you'll get there's a mismatch here. Some of this data in this column is object, and some of it is NaN, basically. I didn't have to do that with Parquet because Parquet actually encodes D-type information, among other things, in its file format. So here I can just say, hey, here's the data set. Please read this for me, Dask. And I get my D-types. And notice actually that some of these are, that were objects before, actually have more efficient representation here. So before, these date times, if you recall, were all stored as objects. They were just stored as strings. Parquet knows these things are datetime objects, and it can store that information in the metadata for the file. So what that means is I can actually, I'm commenting out this step too. I'm keeping it here for completeness because this was in the original pre-processing step, but I don't have to convert those to date times anymore because Parquet's metadata handling did that heavy lifting for me. All the other code here is exactly the same, but that was the one difference. Okay, so let's go ahead and persist that data set into memory now. Yeah. So now we're reading things in here. How long did it take me to read in my CSV data set before? 50 seconds? Okay, great. Let me see how long this takes. Okay, this took 21 seconds. So that was a lot faster. So this is the kind of storing your data efficiently. This is the kind of performance benefits you can get. And remember, that's often a bottleneck in computations. That's often a large part of workflows. Okay, so now let's go ahead and do the other computations we've been running before and see what those times are. Again, we're computing this mean and the group bys. 6 seconds, 4 seconds, and 8 seconds. That's roughly the same as before. So we actually didn't see any performance improvements here in our computations. In the actual, again, the I/O was much faster because I was using Parquet instead of CSV. But once the data is actually loaded into a data frame representation, like we now have a bunch of small pandas data frames, and pandas doesn't care where these things come from. It doesn't matter if it came from a CSV file or a Parquet file. It matters how am I representing this in memory. And in both these cases, it's the same. So we don't see a performance improvement here. So we get I/O improvements when switching our file format. That being said, we can sort of push on further and talk about how we can change the actual graph structure here to make the computations themselves faster. So the next thing we want to talk about is partition size. So remember the partition in the Dask data frame, whereas we're going together a bunch of pandas data frames or QDF data frames, a bunch of tiny data frames we're sort of coordinating computations with. So the partition size is just like how big are the individual pandas data frames that are comprising our Dask data frame. So here I'm going to go ahead and compute that. So you can, I guess we'll do some live coding here. If you want to, I've got my Dask data frame here. There's this partitions indexer thing you can do to get the partitions. I want to get the first partition. It's still lazy. I have to call compute to compute it. But if I did, that would give me the pandas data frame that is that 0th partition, or the first one, for example. So what I'm going to do is down here, I am going to go ahead and compute that first partition. And then I'm going to just I'm going to use pandas memory usage method to just get how big is this thing in memory. And then I'm going to hand that off to this little utility function in Dask, which it's totally optional. Don't have to do this, but it'll just make it look nice. So it's 8 megabytes. That's how big this partition is. For people who are uncalibrated, that is tiny. 8 megabytes is a very small amount of data. So when I was doing, so this results in a really big task graph. So for example, if I do something like, again, live coding, maybe I'm going to abort this portion very quickly if things go wrong. But up here is my first computation. So let me grab that, go down here, and okay, so there's the actual thing. Still lazy, I've not called compute yet. Let's get its Dask object and see how many tasks are in this thing by doing that. Okay, so there are 23,000 tasks in this particular one. I don't know how many are in the group by ones. We could do the same thing for them as well. We'll just revisit this number in a little bit. So these are small partitions. So what I'm going to do is make them bigger. So before when I was running things in the task stream, there was lots of white space happening on the dashboard. That's something you want to try to avoid. When there's white space in the task stream, that means computations aren't happening. Your cluster is idle for that time. So what's happening when you have really small partitions is there are lots and lots of tasks, which each task has a small but non-zero overhead for Dask. The scheduler has to say, hey, worker, run this thing for me. Let me know when you get it. The worker has to then run it and say, hey, scheduler, I have the result. Just so you know, whenever someone asks for it, come to me for that result. There's some overhead to that exchange. When you have a bunch of really, really tiny tasks that are partitions, which result in lots of tasks firing off, that overhead becomes a significant factor in your computation. So what a good partition size is will vary for the particular workflow and for the data set you're using, because you also need to be able to fit the partitions into memory on your workers when you're doing computations. So that's the actual true answer is it depends. In practice, we see that hundreds of megabytes is a good size. It's certainly a good starting point for your partitions. Again, it'll vary on your hardware, it'll vary on your problem, but like start with 100 megabytes or something around there, 200, 300 megabytes. So what we're doing here is we're telling Dask to take a data frame and repartition things such that the partitions are around 100 megabytes here. So all this red stuff here is us transferring dependencies from one worker to the other so that we can then merge them together, because these are all tiny partitions, so we can merge them together on a worker such that they're around 100 megabytes. So what this means is we have bigger partitions, but far fewer of them. So I can now, on my new repartitioned data frame, I can get the first partition and see how big that thing is. So now it's 98 megabytes. Before it was, remember, like 8. Now it's 98. So let's go back to our sort of live coding session. I'm now curious how many tasks are in this graph. So now that I have my bigger partitions, my graph is much smaller. Before it had 23,000 tasks. Now it only has 2,000 tasks. If I did the group by thing, the same message would apply. So let's run these now on our data set. Again, same data set, just partitioned differently. Okay, that actually happened. I did not mess this up. It was very fast. The partitions can play a big role in the performance. So what was this before the partition? 4 seconds? 4 6 seconds or something like that. And now we're down to, under 1 second. So factor of, I don't know, 5, 6. That was fast, and that was fast. Notice, like when I go up here, there's not a lot of white space in the, well, that actually flew by too fast. And when I go here, there's like a large block of like solid stuff happening here. There's not a lot of white space that's peppered in through there where the cluster is idle. The whole point of having the larger partitions is that you're giving your workers enough to actually work on, where the task overhead is a small fraction there. It doesn't really come into play into the computation overall. Okay, I'm going to pause at this point. Any questions? Yeah.
So we talked about how there's the chunk for the XRA, or for the DAS version of NumPy, and the partition for the DAS version of pandas. Is there a similar thing for the DAS version of XRA?
XArray uses Dask under the hood. So XArray data sets are backed by Dask DataFrames, I think, and Dask.
They're all backed by
Dask array. Okay, they're all backed by Dask arrays under the hood. Is a Dask array under the hood. If you take an XArray data array and what do you do? .data, you get the Dask array under the hood.
So you can do some X-ray stuff. So you can do some Dask stuff like just on the X-ray object. But if you need to do like really Dask stuff that isn't exposed at the X-ray level, you can do .data, and that's just a Dask array.
Yeah. Yeah. So like here for I'm focusing on Dask DataFrame here, but like for example, the like store data efficiently, when I said for tabular data sets use Parquet, the recommendation is use ZAR for array-like data. That's sort of the, not technically, but yeah, conceptually equivalent there. And then all the like, make the task graph, make the partitions. Also 100 megabytes is a good starting place for array workloads as well. So that is also a good place for your geospatial things. Okay. So here, what we were doing is making the graph a lot smaller. We weren't actually focusing on making the tasks themselves faster. We just gave the tasks more data to work on to really saturate our workers effectively. But we can sort of improve things more at the actual task level. So we're still going to give them more data to work on, but now we're going to make the actual tasks themselves faster. We're going to do that from using efficient data types. So here is my data set here. So notice I've got float 32 and 32. There's not much you're going to do there to make that faster. But I do have some Python strings here, and I also have an object string down here. So recent versions of Dask and Pandas, like specifically Pandas 2.0 and greater, have improved support for PyArrow-D types. So all of these are backed by either NumPy or just like objects. So I should say, even though this thing says string Python, if I go and grab one of those columns. So like, for example, if I look at this thing, its D type is string Python, but that is just a type, maybe? Yeah, okay, there we go. That's just a thin wrapper for Python strings. So these are just objects under the hood. If I do MRO, I get, yeah, these are objects, basically. It has a nice wrapper, but they're still just backed by Python objects. So circling back to the PyArrow D types. So the one that I want to really focus on is PyArrow strings. So all the D types that you can express in PyArrow, you can now express in pandas. So you can have a PyArrow 64 float or a PyArrow 8 int or something like that. You can now keep those things in pandas. And because you can have them in pandas, you can also have them in Dask, which is just lots of pandas. The thing I want to focus on here is converting from Python objects to PyArrow strings. In short, like NumPy is already pretty good at working with numerical data. So you can switch to PyArrow, but you won't see large performance impacts. You will see large performance impacts when you can get rid of Python objects. So here I have some, I'm taking these string columns and I'm just converting them using as type to be PyArrow string, and then I'm repersisting the data set. Watch the memory go down on the worker memory stored plot. So PyArrow strings are much more efficient than Python objects in terms of their memory footprint and their computation speed. So now if I look at my data types, those columns that I specifically casted, so this one, and this bottom one down here, are now PyArrow strings. Let's see what that did to our partition size. So what was our partition size before? It was like, yeah, 98? Okay, great. So now our partition size is, it's bringing it back into memory. So that's taking a while. Oh, yeah. Yeah, I'm not sure what's happening here.
Yeah, also the dashboard didn't go down. That happened
Emoji.
to me like once, but then it couldn't replicate.
Yeah. Okay. I'm not sure what's happening here. This is taking a little bit away from the punch because we're like at the end of the notebook. I am going to go ahead and kill this. I'm going to look at my cluster and see that it's ready. Okay, great. I'm going to see if I still have this. I still have things stored in memory. Okay. What if I redo this? I get an answer. Great. What if I run the cell again? Okay, editor, please edit that out of the YouTube video. So before it was, what'd you say, 98 megabytes? Now it's 45, so so that's a significant reduction in memory of the partition. And remember, I just casted 3 of the columns to be PyArrow strings there. So just casting those 3 columns gives me a significant reduction in my data set size. I'm now going to repartition back to 100 megabytes to get something that is reasonable there, and persist that into memory. And now I'm going to do my final computations here. Again, same computations. They're now much faster though, or they're faster by like a little bit because they were already really fast to start with. But we've now made our tasks themselves faster because they're operating on PyArrow strings. Yeah.
Why do you have to repartition there? Like the DDF you're working on had already been.
Yeah, I don't have to. I could have done that. It's just the partitions were smaller, so I'm liking to stay at that 100 megabyte thing. But you're right, I can skip that cell if I wanted to. Yeah. And also honestly, the 40 megabytes aren't that small, so like probably the overhead's okay there. The task overhead before the like 10 megabytes was very small. Yeah.
So a lot of what we're doing here is optimizing against known parameters of the cluster we're playing using PLDs. What if you want to share your data processing with people for whom you don't really know what compute power they might have at their disposal?
Yeah.
What are best practices or sort of known parameters you might expect from people, how they can handle data like that?
Yeah, that's a great question. I'm going to re-say things I've already said. Just hope that's okay as the answer. So in general, file format, Parquet is a good one to go with. There's always exceptions to rules, but Parquet is a good one to go with. Again, for tabular data, for array data, use ZAR. And then, yeah, hundreds of megabytes is, again, always edge cases. People might have weird machines, but if you're just going to pick something out of a hat, 100, 200 megabytes is a good place to be for your partition or chunk sizes, whatever type of data you're working with. So again, I'm just kind of re-saying the things, but I think I'm answering your question a little bit. Great.
So what you are not saying again is that 100 megabytes is not for fancy pants clusters. It's a good, it's a good,
It works well broadly.
right.
Yes. Yeah.
I guess another way to express it is to talk about the overhead per task.
Mhm.
If I get it correctly, it's of the order of 100 milliseconds. Is that correct? Is this a rough guideline? And I guess that depends on, of course, like how close your developability to your cluster and all of these things. Kind of what are the rough overheads per
Yeah, I forget off the top of my head. Does
300 according to the doc, but
300 milliseconds?
milliseconds, but it could be a made-up number.
Yeah, I don't remember off the top of my head. Yeah.
I think this is if your user can say, okay, my task overhead is roughly this, then I guess that your user. Obviously, there must be other parameters like how many of these chunks do you want to task or something.
I had a workflows that the best partition size that worked for them on the cluster was like a gigabyte. So it's like, yeah, sure. But maybe a gigabyte, we say, if you don't know what's the hardware, then maybe a gig might kill your worker or something like that. So
Yeah.
100 megabyte, I think it's like a one.
It's a
It might not be the most optimal.
it's a relatively robust rule of thumb.
So
Yeah.
the docs are, I just Googled it, the docs say between 200 microseconds and a millisecond or whatever.
1 millisecond.
Yeah.
Yeah, so
Yeah.
it's not much, but when your task graph is
When you're really big, your tasks are really fast also. Like Charles is here. He works at NVIDIA. GPUs are really fast. Other things become bottlenecks when your compute becomes really fast. Things like I/O become a bigger bottleneck. Things like tasks overheads become bigger. So, yeah. Real quick, last thing I wanted to touch base on was Pyro strings. We saw the sort of impact they have here. So in Dask today, you can set this config value, DataFrame convert string true, and it'll automatically cast your data sets to use Pyro strings if they have text data inside of them. So you don't have to do something like this. You totally can. This as type I did, that's totally valid. You can do it. People tend to not want to do that. They just want to say read CSV and please do the right thing. It will automatically cast your data sets to use Pyro strings. I should also say in an upcoming release, possibly next Friday, this will be the default for this. This is off today. It will be the new default soon. So yeah, with that, I'll maybe wrap things up. So there are a few things here that we talked about for performance. We played around with the dashboard some. We got to see what was going on there, kind of hopefully get a sense for what's happening on our cluster, or at least know that what's happening on our cluster is represented here in these plots. We talked about partitioning your data well. We talked about storing your data efficiently in file formats. We talked about using data types, efficient data types like Pyro strings. We talked about persisting your data set when it makes sense, when you can fit on your cluster and when you're going to do repeated computations. And I think, what was the last thing we talked about? Computing multiple things at the same time. So these are good practices to go out with when you're wanting to optimize performance on workflows. Here are links. There are repositories for Dask and distributed here on GitHub. We have docs pages here. If you have a Dask usage question, feel free to jump on to the Dask discourse. And if you run into a bug, have a feature request, want to engage technically, feel free to jump over to the Dask issue tracker and open something up there. And if you want to get involved, feel free to go look at our contributing guide. Totally open source project, community led. We would love to have you. Okay, with that, thanks everyone.
I'll be here during sprints too.
Oh, cool. Yeah, Julie will be here during sprints. With that, thanks everyone. I'm curious what questions you might have. Oh, thanks.
Dask, pandas, and Pyaro, there's going to be a bug on Thursday at 1:15 about like all the connection and interactions with all this stuff.
Yeah,
James and-
there's a buff on pyro strings and pandas and Dask on Thursday. Yeah, so if you're interested in the topic, it's after lunch. Feel free to swing by. Any questions that folks have? Also, thanks for all the questions so far. It's been good engaging. Yeah. Oh, you want to?
I guess one thing I've always been keen on is being able to visualize a task graph for working with the data, working with a data array.
Mhm.
But I've had a time difficulty visualizing it. Is that just because of the sheer number of points for like a grid or data set or an array type data set that's hard to visualize a task graph? It doesn't visualize the same way.
Yeah, like it looks ugly.
Yeah.
Yeah. There's also a dashboard tab for the graph that might be better for like very large graphs. It's called graph. But it's ephemeral, so you only see it while it's running. But it's kind of a nice. You got it? Yeah, it's only while it's running. Or if you want to run. No.
Oh no,
Max is
it's
out.
too big because I have all the partitions persisted. But yeah.
It does max out as well, but it's sometimes works better than visualize.
Depending on what you're wanting, you can also not look at the individual tasks, but you can look at the high-level graph. You can do things like this. So that's my thing. You can like visualize from a high level too. You don't have to visualize the low-level tasks. You can visualize the, sort of chunks. Well, this is a really bad example. Well, no, it's a good example. Look at that. You can look at just the high-level things. This sort of corresponds to operations. So here's like a repartition step. Here's a get item step. It's not showing the get item from 1,000 partitions. It's showing get item. It's a better way to represent full things. Yeah, sure. Go for it.
There's like a groups tab too, but that would be in a higher level. You can see like a graph of the task group, but that's also when it's running.
There's also this view. I don't know if anyone showed this yet, but this is this is a display of the graph. So we sometimes think of graphs like dicts, but they're actually this other structure that's kind of dict-like, and this shows like the layers. So what James was just showing was the visualization of this, but you can also just look at this to see like the different layers of computation, and that might be useful for arrays because it'll show you the array repr will show up in here. So you can see that changing shape as it goes through the different layers if you drill down into this thing.
Awesome, thank you. It's a really great start.
Yeah, it's .dask.
What other questions are there? Yeah.
I guess this is probably moot since you said there's a change being pushed, but let's say I wanted to make that change to use Pyro or some other kind of thing like that as part of a repository to force that behavior and package that we have. Is there a preferred way to do that? I know that Dask has some big files, but
Yeah.
kind of curious what your thoughts are on that.
Yeah, I would set this config value, and I think what you're saying is there's lots of ways to do that. So it depends on the particular system. Like one thing you can do is this might seem hacky. You can like in the init file for that package put that code, for example, or you can set the corresponding environment variable. Or I'm not sure what would work best for the system you're talking about, but yeah, there are several ways you can set config values, but that should be all you need to do. Yeah.
One question.
Sure.
First of all, thanks a lot for the great tutorial. It was really neat. And I was wondering first, how is memory distributed? So, for example, if my nodes have maybe it's
One more time.
So let's say if my remote worker nodes are connected over the InfiniBand network,
Mm-hmm.
can Dask take advantage of that?
Yes, Dask can. We see that more often in GPU usage. Yeah.
Right. And then the second question is, so this you showed now a lot about let's say things that have to do with arrays.
Mhm.
But I guess you can use Dask for pretty much any kind of task that you want to parallelize for workers. And there's
Yeah.
are there any other communities besides? Yeah, you mentioned Bio, I think briefly. So what kind of other things are people doing with Dask?
Oh, yeah, so Dask is a general computation engine. It has nice APIs that are familiar to like SciPy folks, like NumPy and pandas APIs. But yeah, you can delay computations. You can say, Dask, please run this function for me, and it will do it. So the question is like, what do people use that for?
Yeah, exactly. Any like other communities using that building their workflow.
There's yeah. There's lots of things. There's like other systems too that are built on top of Dask. Prefect is a sort of like workflow management system, kind of like Airflow, and it itself builds on top of Dask to handle its coordination. And yeah, we run into people using Dask in all sorts of ways. I bet lots of folks here, well, several folks here have already said X-array, so I'm assuming that means like a geospatial thing. It's really common in the Earth sciences space. I'm sure there are Pangeans here who use Dask because of that. But yeah. Yeah, machine learning, XGBoost. Lots of libraries have integrations with Dask. Things like XGBoost. If you could use xgboost.dask. You see it in finance. You see it in, like, I've seen some sports modeling people recently. So that's, I enjoy sport, so that's good. Yeah.
Does the compute load for each task have to be practical? Like, is it possible at all? I'm not sure. This might be way out there.
Yeah.
But could you, like, have the task compute load be anything outside of Python, like a sub-process and executing that as default?
Yeah. So the no is sort of the answer. It's Python library. We have to submit Python tasks to run. You can make that Python task do whatever you want though. So yeah, if you wanna subprocess.run craziness, you totally can do that. Yeah. I don't know if I'd recommend that, but one could do that.
What is the hard required API for a task control? Is it like a function that
Yeah.
is called and you can do whatever?
You can give it whatever function, whatever inputs, yeah. There are some requirements around serialization. We do send functions and things from one machine to the other. I do have to be able to, one has to be able to like pickle this thing. You use Cloud Pickle, yeah. So that's kind of the only hard requirement there. Yeah. Does that answer your question?
So when you say you're automatically mirroring the environment to the workers, when startup clusters create the current.
Yeah, that is a coiled specific thing though. The software environment, the like Dask thing is the software environments need to match. On the client machine, on the scheduler, and on the workers, you need to have the same version of the same packages installed everywhere. Depending on how you deploy, Coiled will do that automatically for you. Other, like Dask Cloud Provider, you bring Docker images. So if you have some people have teams around them who manage their fleet of Docker images. And if that's the case, then you can totally just say, Dask Cloud Provider, here's my software. Please use that.
So I'm not aware of any people that have tried doing this in Dask or non-Python payloads.
People mine Bitcoin every once in a while. Yeah. Yeah.
We might want to ask everyone to shut down the clusters that are not connected so they don't stay up.
Oh yeah. Okay.
Clusters.
Yeah. So if folks could, I guess locally, if you want to, if you have a notebook, a coiled notebook running, if you just want to, like you're in Jupyter, Control C that, it'll shut down things automatically.
Could you shut down the clusters?
Yeah.
From the notebook?
We'll find out. That's fine.
We'll find out. Okay,
So, any other questions? Yeah.
So for the compute part that you said, compute multiple things at the same time.
Yeah.
Does it work if one of the variables depends on the other one?
Yes, it'll still work. Yeah. Yeah. Dask will determine that. It will just kind of that will work. Yeah.
And what if you want to
It will run that kind of in serial. It'll have to compute the first thing before it can compute the thing that depends on that, though.
the order of things doesn't matter when you compute?
Oh no. Yeah, it merge. Yeah, you mean like A depends on B? Can I say compute B comma A? Yeah, no, it's a.
Clear that. And then what if one of them do not fit in the memory? Is there a way to optimize that situation so that let's say you let one of them like they click on do pre-processing on the big data sample from that
Mhm.
and maybe feed the model and then apply a model to the big data.
Yeah, you can do things to put dependencies there. Honestly, I would just not use Dask compute there. I would compute them separately. I would say do the first thing, now I have my model now, or whatever in the particular example, now I can do the next thing. I wouldn't use Dask compute. You can set up dependencies so Dask knows, oh, I have to compute this before I compute this. But yeah, I would just recommend doing them sequentially in that way.
That would require to do everything twice, right?
You can like persist a thing that you might be sharing later on. Yeah. I might be not understanding the question.
So
I'm realizing.
You have a big data set with some pre-processing.
Yeah.
And then from the pre-processed data, you put the sample
Yes.
to develop a model
Mhm.
and apply the model to the big data
Mhm.
and then export your results.
Yes.
So the data that you sample is pre-processed, and the data you want to apply the model to is pre-processed.
Mhm.
And you want to do this once. How it works? So the sample data you can compute
Mhm.
small, and then develop the model, and you apply a model.
Mhm.
But the big data itself doesn't fit in the memory, so you need to.
I see what you're saying. Yeah, I'm not sure off the top of my head. Yeah.
And it doesn't fit in the worker memory either?
You can't use persist in that context. It does need to fit onto the clusters, the full cluster's memory. Yeah. Thank you for the question. Yeah.
Are there different strategies available for how tasks are submitted to workers? Like, I'm thinking more like normalized inter-worker communication, those sorts of things.
Yes. I think the best I can do here is like point you to documentation that is written. But yes, things like that are tasks are co-located. There is thought that goes into that. Yeah.
And follow-up, does that also take into account like hardware as well? If you have multiple workers on, say, a node, and you want to optimize inter-node, for example?
I don't know if that's taken into account. Oftentimes we see workers on individual nodes. It doesn't have to be that case, but oftentimes it is. So yeah, I'm not sure if that's taken into account. Like the host name or whatever for the machine. I'm not sure. Yeah.
So one of the things that Xarray like explicitly say
Mhm.
is if you have data that you're reading over multiple files, not to read each chunk that. For my personal workflow, most of the files that I have are 30 megabytes or less. Would it make sense to then maybe reprocess all that data into files that are a bit larger, maybe based on the larger time scales you're putting up species then to get the rechunking?
I don't fully understand the question.
We talked about doing things like getting it up to maybe like 100 megabytes
Mhm.
or more.
Yeah.
For my personal workflow, I've got a server that has like a terabyte of memory, but I'm not going to want to load all of that, maybe take it away from other users. So 30 megabytes still on a kind of small size, we want to increase that since a month is maybe a chunk.
I think 30 megabytes sounds like an okay size. If you don't, like, it's the same order of magnitude, roughly, right? Another thing, if you don't want to repartition your data, another thing you can do is, well, one, you can always repartition to multiples, and that should be fast because it's just reading multiple chunks from your original data set, if that's possible. And I think there might be like there might be a helper function that's like scale my clusters, my chunks by 2 or something. I think that exists in an X-ray. But another option if you want to write a custom operation is you can take multiple chunks. You can read in multiple chunks at once, or you can do analysis on multiple chunks at once. Does that make sense at all? Kind of.
Yeah, I'm following.
Okay.
Yeah.
Yes, I connected to some of the questions that I work on earth science side and developing PDB solver.
Mhm.
So what we write in a lot of matrices and vectors are sparse. So we generate like a SciPy sparse
Mhm.
matrices. And then on that level, we have a lot of matrix vector multiplication. It seems like there's some options in Dask to use a sparse array,
Mhm.
but it seems like I can't really do the matrix vector. That's like the as you do in a dense matrix sense.
Yeah.
But are there any plans to sort of like add more on that sparse matrix vector operation using Dask parallelization?
What you're saying is like I have like a Dask array backed by sparse things and a Dask array backed by non-sparse dense NumPy things, and I can't operate those together.
Yes, so say I have a sparse
Yeah.
my sparse array,
Yeah.
Sparse matrix.
Sure.
And then I have a vector. I
Mhm.
want to do a matrix vector multiplication. But currently, Dask has an implementation that if that matrix is dense,
Yeah.
then you can do a chunk and you
Yeah,
can
yeah.
parallelize it into making Dask.
Yep.
But like if you have a sparse array or sparse matrix, you cannot do that, as far as I understand.
Yeah. I'm not sure. So yeah, there are no current plans. That doesn't mean there couldn't be in the future. If a large user group came to us and said, this will make our lives a lot better, yeah. Hopefully that non-answer is helpful. Yeah. Yeah.
We can open an issue.
Yeah.
We'll try.
Any other questions? Yeah.
At the beginning of the tutorial, I was asking a question about working on a cluster that might have multiple nodes and how to set that up. In a minute, could somebody give me a hand trying to do that? Because I have a connection to one and
Sure.
trying to do things I learned here. I need one.
Sure. Yeah.
I can follow up on my question, how can you reference a data frame that you persisted on another client?
Yeah, so use this thing. This is like named data. Oh, that's way too small. These are like named data sets. Publish data set. You can like have, here's a nice example. You can read in some data, persist it, and then basically give it a name. And then other people can then list those data sets and get that data set by name. I think this is what you're talking about. Yeah. There's a much more complicated answer to this too, but do this instead. You can like create the futures on a different machine because it just needs the name of the task. And now you have a pointer to if the cluster has the data, it'll say, oh, cool, I know what that key is. But that's useful for individual tasks, but not, it's a pain to work with for large collections where you have thousands and thousands of tasks. So I would use the publish dataset API for that case. Yeah.
One quick question about every once in a while I get like a file that randomly shows up. There'll be a core period and an error, and it usually happens after like one of my workers fails or something else like that. Is there a built-in thing with Dask where it basically drops, if it can't reassign that data, it drops it out as like a saved file? Okay, I'm trying to narrow it down. I think it might be a Dask.
I'm not sure if I can help with the narrowing here. Yeah.
Don't think it's that.
Okay, cool, that works.
Yeah.
So there should
Fair
be a
enough.
Dask workspace folder that creates it. I don't think
Yeah.
it's called core.anything.
Helping my troubleshooting. Appreciate it.
There we go. I guess we are helping a little bit with the narrowing. Yeah.
So I can put files when I exceed memory limits when I'm working on PC resources. So the core file is just memory being dumped to disk.
Oh, okay.
So I would try to reduce your memory usage for each task.
I appreciate that, thank you.
That sounds good.
Any other questions? Thanks everyone for coming. Thanks for all the engagement. Really appreciate it. And yeah, have a good rest of SciPy.